Okay, we are recording. Great. Okay, so what I want to do today is finish up the last thing that'll be on your exam. And in some sense, you kind of already know it because we've actually done a corresponding thing in the electric case. I want to take a magnetic moment and put it in a B field and see that we get a torque. So let's do a little review. Recall, so what we want to do is what happens if we place a magnetic dipole moment in a magnetic field. So I think the first thing we have to do, because it's been a little while since we've done it, is recall what a magnetic dipole moment is. So I ask you, what is a magnetic dipole moment? This is did this early on. The symbol for it was a mu. What was it? Okay, so what we do, this is gonna be a top view here. We have some sort of loop of wire like this. It doesn't matter what it looks like. And it has current. So this is some sort of loop of wire. And it's carrying a current. And so this will be the direction of the current like this. So this is some I. And there's going to be some area of the loop here. So A is the area of the loop. Okay, the magnitude of this quantity here, the magnitude of that is by definition, it's a current flowing in this loop times the area of the loop A. We did that quite a ways ago when we had the circular loop in the XY plane and we were trying to find the magnetic field along the Z-axis using Biot-Savart law. We had that. Now, here's an even an equally old memory. How did we define the direction of this? Okay, so the definition of magnetic moment is you have a loop of wire. It's carrying a current I, and there's some area here A. So that's the definition of it. Now, we also had a right-hand rule for that. And what was our right-hand rule for the magnetic moment here? In other words, if this is our magnetic moment, our magnetic dipole moment, what is going to be the direction of the mu for this? Here's my right hand. What will I do? I'm going to take my fingers here. I'm going to wrap my fingers in the direction the current goes. So the current is going, the net circulation is like this. So I'm going to wrap my hands in the direction here like that. And my thumb points in the direction of mu. And yes, and there's that delay, but what you said, Everett, is completely correct. So you wrap your fingers like this, and your thumb points in the direction of the magnetic moment. And so this right here is the mu for this. And it's going to be perpendicular to that plane. So the question is, if I were to have something like this, if I were to put that into an external field, so imagine now I have my little loop. So here, imagine this is kind of now a side view. So let's say I have a magnetic field going like this. This is some sort of external field. So that's an external B field. And I'm going to take that loop here, and on the side view, you know, might like something like, who knows, like that. That's going to have a mu like this. Okay, so that's a little hard to see. So let's say here with this little paper towel here. Let's say this is a square rectangular loop. So I have current going like this. I wrap my hand in the direction, this is the mu. Now imagine I put this in a magnetic field. So imagine there's a magnetic field coming up out of the board like this. This is at some sort of angle like this. So here's my mu. Here's the B field. That's what this picture is supposed to represent. The question is, what happens to this fellow here? Okay, so what I'm going to do is I'm going to give you the answer, then I'm going to go through and prove it. what we're going to find out is that the magnetic field exerts a torque on mu given by, okay, tau is always the torque, mu cross B. So we're going to have to do another cross product part here. And what we're going to find out is that that magnetic field, that torque, is going to try to take that mu and align it with the field. So the torque attempts to align the mu with the field. And that's what we want to prove. And again, this looks exactly like, remember when we had the electric dipole moment? And let's just do a little review here. Recall, this looks just like the electric dipole moment in an E field. Okay, so let's do a little review. How did we define electric dipole moment? Remember, we had a P. This is our electric dipole moment. And how did we define the electric dipole moment? This is a definition. Okay, so this is what we did. Remember, we had two charges. We had a negative charge, so minus Q. And then we had a positive charge plus Q, like that. And there was some separation distance between the two, which we called R. So this is the separation distance here, R. Right? Separation distance. And the R by definition goes from the minus to the plus here. So here's this minus charge, here's this plus charge. This right here, the magnitude of this is given by the one of the charges. It's not both of them because the total charge would be 0. You take one of the charges times the separation distance, R. I think we were calling it D before. And this P points from the negative to the positive. So the P for this, if here's a negative charge and if here's a positive charge, that P points along the direction here like this. Okay, so this P is really this Q times R. This Q is taken to be the positive one. So P goes from the negative to the positive one. That's the definition of electric dipole moment. And we ask what happens if we have an electric field here like this. And if we place this little P here like this. So here's our negative charge and here's this little positive charge. All right. And what did we say happens? Well, we said that that electric field puts a torque on that P, and it's given by P cross D. So in this case, we have P cross D, but in the magnetic case, we have mu cross B. So the two look just like each other. One's the, this is the electric version, and this is the magnetic version. And again, that the torque from that E field tries to take that P and align it with the field. So what we're going to do is we're going to derive this. I'm going to take a special loop because it turns out if you take a generic loop, it's that's tricky to show. So we're going to take a rectangular loop, and I want to show you that this pops right out here. Okay, so I'm going to pause there. Are there any questions with this? Okay, so let's do, again, a little more review. Let's review torques again. I know we've done this before, but it's always good to review. So remember in first semester physics, what did we do? How did we define a torque? Well, we took a stick here. This is some sort of stick. And we put a pivot here. So we said this is going to be pivoted here. So here's your pivot. And then we put some force here like this. That was some force. So imagine here's a ruler. Somehow you nail it to the wall, or you put a pivot here. You apply a force coming off at some weird angle there. Okay, from the pivot to where that force is applied, we call that R, and this is your moment. This is the definition of the moment arm. The moment arm, by definition, goes from the pivot to where that force is applied. And we ask which part of that force is going to cause that to rotate. So we took our force and we broke it up into components. We call this part F parallel. This is F parallel is the part of the force parallel to the rod. We call this F perpendicular. So F perpendicular is a force perpendicular to the rod. We said which one of these causes the rotation. Well, it's this F perpendicular. So the F perpendicular causes the rotation. And this is theta here. And so we defined the torque, and the symbol for torque is a tau. We're just doing the magnitude of it. And how did we define this to be? Well, it has to be related to the F perpendicular. But if I took this force and actually applied it right to the pivot, that wouldn't rotate. So somehow a torque actually has to be connected with this moment arm. And so we defined it to be this F perpendicular times the distance from the moment arm, which is this like that. That was our fundamental definition of torque. And what did we say about F perpendicular? Well, if this is F magnitude here, that's magnitude of F. If this is theta, this side here is our F sine of theta, like that, which I could write then as in this F, or I'll write it like this, R F sine of theta. And this is by definition the magnitude of the cross product or cross stuff. So if you have one force acting on an object, the torque is given by R across stuff. So what we're going to do is we're going to use this idea here and apply it to a loop. And I'm going to assume that my loop is actually a square. So imagine, should I write on this? I don't know. Oh, can I have a piece of paper, sir? Thank you. Okay, so let's say here's my loop. And so I'm going to draw a current like this. So here's my rectangular loop in the blue. Let's say I have current going like this. Okay, so this is my current loop. Imagine this isn't a piece of paper. Imagine it's wire in the shape of a rectangle, and that represented by that blue line, and then the current's going like this. And what we're going to do, we're going to put that in a magnetic field. So put this over here. So let's ask what happens when our rectangular current loop is placed in an external B field. So I'm going to draw out kind of two versions of this. So here's our external B field B. And we're going to put that loop in it like that. Oh, I was going to do the generator problem for you too, wasn't I? Oh, well, we'll get to that in a second. We'll do that afterwards. So this is kind of a yucky side view. Right, going like this. That's hard to see what's going on. A better side view would be the following. A true side view would be this. So a better side view would be this. Is that it had the wire like that. And so imagine this is, so it's kind of like this. That's what we're looking at here. Okay. Ah, my daughter just corrected me on my current. Thank you. There. Okay. We have that. So that's what we would have here. Okay. I'm going to pause here because the geometry can be a little confusing. Does that make sense? Okay, getting a yes. Okay, so what we're gonna do now is we're gonna label things. This is gonna be side 1 of the wire, side 2 of the wire, side 3 of the wire, and side 4 of the wire. So it's a little tricky about this diagram is labeling the pieces here. So where is side 1 here? Okay, again, here's my loop that I'm putting in a B field. This right here is my side 1. Okay, so I'm gonna put a little circle there, and you can see if I have the current going like this, okay, I don't know, you can see that the arrow's coming this way. If I go like that, that current's coming out at me. So this right here, I'm gonna put a dot there, and that's my side 1 right there. Okay? Now, where would side 2? It's this current coming down here. So again, it's coming down here like this. So if it's like that, this right here is the second wire. It's this wire right here. Now, where's this third wire? Well, again, it's gonna be this part here. If I go like that, you can see that's going into the board. So that's going in here, that's side 3. And now where's side 4? Well, this is side 4, and you can see if you're looking at it like this straight line is also functioning as side 4. So I'll put an arrow like that. That's a little on the confusing side, and that's side 4. So it's like this again. So that current's coming up like this, like that, and that's what that represents. Okay. Does that diagram make sense? If that makes sense, then everything else is going to come out pretty easy. Okay, I'm taking that to mean that it makes sense. Okay, so let's figure out how the mu is going to go with this. Now remember, what was our right-hand rule for this? Our right-hand rule for this was you take your fingers and you wrap it in the direction that the direction the current goes, and your thumb points in the direction of mu, and it's perpendicular to your current loop. So if I were to do that, that current comes out like this. So if I were to wrap my hands in that direction here, my mu is actually going to be like that. And it's perpendicular to that current loop. And that's my mu. So now let's go through and calculate all the torques on it. Okay, let's look at wire 1. And it's going to be easier to use this diagram here. How are we going to find the force? These are current carrying wires. So what do we know? We know that the force on a current carrying wire is IL cross B. Okay? So what is going to be the direction of the force on wire 1 coming out of the board? So let's just do side 1 here. Up, down, right, left, in, out, spiral. What does it do? On this side right here, on this side here. I'm hearing to the left. And actually, that's correct. Again, remember, L's in the same direction as I. So if I look right here, that I is coming out of the board like this. So I point my thumb in the direction like this, and then I have to bend them in the direction of B where I can't do that. So I have to turn my hand, so it's L, crossed into B, right? Does that make sense? Let's put this here, right? So if it's like this, again, this side, this is my current. This is coming out at you, so it's L, crossed into B, it comes out like that. That's the force on side 1. And again, remember what has to happen here is that whenever you have a cross product, this has to be perpendicular to the two vectors making it up. Okay, now let's do side 3. Well, if I do the same thing for side 3, what am I going to do? Well, the L is going into the board because the I is going into the board. So it's L, crossed into B, and it's like that. So this has to be the force on side 3. Now, what's happening on side 2? Again, side 2 is the current that's going like that. What's the direction for that? In, up, down, right, left? I'm hearing out, and that's correct. So on side 2, if you do L, right, because that's the direction of I, crossed into B, your thumb's coming out. So side 2 is out. Okay, finish it up. We need side 4. Yes, side 4 is going to be going into the board. Again, because if we did the L cross into B like that, that's going into the board. 2 and 4 cancel. So the force 2 and force 4 cancel. Okay? But guess what? Force 1 and force 3 also cancel. Right? Because that loop isn't moving this way or that way. Okay. They cancel, but what do force 1 and force 3 do that forces 2 and forces 4 don't? Yes, they supply a torque. So you can see right here that 1 and 3 are not going to be a torque, supply torque here, but this one will. So what happens here, if I go back to here, we have the force on this side here pulling to the left. The force on this side over here pointing to the right. So it's going to take that and it's going to go like that and try to align it. So I'm going to redraw this picture over here, but with less clutter. And again, this is almost exactly the same proof we had for the electric dipole case. So if I draw that, so we have this guy here, here's this guy, this is our F1, and this is our F3. And this right here is our mu. Okay, that's what we have. So I'm going to say that the net torque, or the total torque, has to be the torque from the first one plus the torque from the third one, meaning on the first side and on the third side. And right here at the center, this is my pivot. So I need some dimensions here. And so what I'm going to say with that, here's my loop here. If this is side 1, 3, 2, and 4, I'm going to say that this length here is L, and this length here is W. Okay. So what is going to be the torque? What is going to be the direction of the torque on the first one, and what's the direction of the torque on the third one? So what is the direction of the torque on for F1, and what is the direction of the torque for F3? Okay, we have to do the torque is R cross F. Oh, okay, got an answer. It is out for F1 and in for F2, F3. What are those I like? If they're in opposite directions, then that they would actually cancel each other and the thing wouldn't rotate. Okay, so let's figure out the R. Remember, the R always, that's your moment arm. R by definition goes from your pivot, here's your pivot, to where that force is applied. Right there, that is R1. So let's do the R cross F for this. So R crossed into F, that's out of the board. So that has to be the torque for the first force out of the board. Okay, everyone agree? Now let's do R cross F for this guy here. So this is R. I call that R3. The magnitudes are the same because this is pivoting about the center. So R cross into F3, that's also out of the board. Okay, they're both out. Okay, does that make sense? Okay, I'm taking that to mean yes. Okay, so what it means here is I can actually just add their magnitudes. Since they're both out, what it means is that they're both in the same direction, so I can just add their magnitude. So I can say the net torque is just going to be the torque from the first fellow plus the torque from the second fellow. So now let's apply the R cross F to this. So this is going to be what? This is going to be the magnitude of R1 cross F1 plus the magnitude of R3 cross F3. So what do we know about a torque? Well, it's going to be, what do we know about a cross product? Well, we know how to break those apart. So I can say our net torque. So what is this? This is going to be magnitude of R, magnitude of F1, sine of theta 1. Okay, where's sine of theta 1? Right here, that's sine of theta 1. Plus R3, magnitude of F3, times the sine of theta 3. Where's theta 3? That's our theta 3 right here. Well, what do we know about this? Well, this R1 is W over 2. Because we're calling this whole length here. Remember in our picture here. This whole length here was W. So if you look at this R here, this magnitude of R1 is W over 2. Okay? That's really kind of hard to read on my screen, at least. Let me redo that. That looks relatively legible. Okay, and then R3 is this guy here. So the magnitude of R3 is W over 2 as well. Okay, now what do we have for this, our friend here? Our friend here is going to have to be the magnitude of this IL cross B. So what is this? This is I, magnitude of L, magnitude of B, times the sign between the two. So if you come over here, what is the angle between L and B? L is coming out of the board, B is going up. That is a 90-degree angle. So this side here is just I, L, B. Like that. And likewise for this, you get the same thing here. If you were to do the magnitude of F3, equaling ILB. This gives you the ILB as well. Same argument. So what happens? These two terms add together. They have the exact same magnitude. So what do we get? We get the torque equals 2, because I got 2 of these. 2 of what? Well, I get this W over 2, this guy here. This guy here is this ILB. Then times this guy here, sine of theta. Okay, I'm gonna let the angles are the same. This theta 1 is the same thing as theta 3 by geometry. So let theta 1 equal theta 3 equal theta. So what happens? Well, the 2's go out. So I can write this as 2. Okay, the 2's cancel. So I can write this as I, W times L. And I think my L keeps on changing from a script to a capital letter. Sorry about that. Okay, B sine theta. Well, what is the width times the length? Well, that's the area of my loop. So this is IA, okay, times B sine of theta, and that's my torque. Well, what is this? Well, that's my definition of mu. So what's this whole thing here? Well, that's really the magnitude of mu, magnitude of B, times the sine of theta. So that's really the magnitude of my mu cross B. That's the proof of this. Now, we derived this for a rectangular loop. The only reason we did a rectangular loop is we can work it out. If you go and take the course at Advanced C&M, and I hope you all do, you'll actually prove this expression in general. It's a little more involved than this, but at this level, this is all we can do, which is pretty cool. Now, I want to show you an application of this to particles. And once we get that, what I want to convince you of is that this, coupled with Faraday's law, is going to be the entire basis for NMR. So I want to show you how that works. Okay. So I want to talk about protons and electrons and neutrons and see how it's connected with this. Okay, so let's say how is this idea of torque related to NMR? Okay, so NMR, first of all, is called nuclear magnetic resonance. And it's in the medical field, you know, that you can often see these absolutely stunning pictures of internal anatomy that's coming from this. In the medical field, what happens is N is scary. And so what you do if something's scary, you drop it. And you just can't call this MR. And so you put an I in here. And so you call it magnetic resonance imaging. Why? Well, because if you have in the word nuclear, that scares people. I'm going to try to convince you the nuclear just is going to refer to the fact that we have a proton and we're flipping its spin. That's all we're doing. Okay, so in medicine, it's called MRI. If you do anything in physics or material science or ceramics, where you actually try to study structure, it's always called NMR. No one says MRI. So if you're, let's say you're in material science, you have to do one of these, you're not going to say you're going to take an MRI of your sample. People just look at you like you're from space. No, you always do an NMR. Okay, so how does this connect to things? So first of all, how can we view particles like protons, neutrons, and electrons? Okay, what I'm going to give you is not true, but it turns out it works really, really well. And in fact, most people, whether they would like to admit it or not, think of this as when they think of a particle. So you can view, okay, it's not, but it's actually, it's not a bad place to start. You can view particles as spinning objects. So in other words, what I'm going to do is I'm going to draw a little ball here like this. I'm going to say that that thing is spinning like that. Well, from first semester physics, if something is spinning, it has angular momentum. So a spinning object has an angular momentum. And so how would we find this? Well, again, remember from first semester physics, if something's spinning like this, you wrap your hand in the direction the thing is spinning, and this would be the direction of the angular momentum. So this is your angular momentum. Okay. Now the angular momentum for a particle, remember how in general physics, we call it L. L is your angular momentum. If you're talking about a particle here, you don't call the angular momentum L. That's going to refer to something else. So what happens is you don't really use L if you're dealing with particles. Instead, you call it S. But it's just like your angular momentum. It's just you're giving it a different symbol. So when you talk about a particle spinning, what you really mean is that you're talking about its angular momentum. Now, let's say this is a proton. What's the crude way of viewing a proton? Well, proton I can view as basically a spinning positive ball of charge, right? Protons have a positive charge, so it spins like that. Well, if it's spinning like this, so imagine you take like a ball and plaster positive charge on it and then spin it. What's happening? Well, that charge on the surface is moving in a loop like this, okay? And that positive charge is moving in a loop, guess what? It's gonna have a magnetic moment. So if you have a positive charge here for a particle, okay, in addition to having an S along that same axis here, it's also gonna have a mu. So this right here is the magnetic moment for a particle. So if you had a proton here, that proton magnetic moment would be aligned along the spin here. Now, if you have an electron, and it turns out that these are related to each other, and there's a way that you can actually relate these. I'm not going to go into it. Again, take our course in, let's see, where would you do this? You do this in a number of places. You do this in advanced D&M. You do this in quantum mechanics. You would do this in modern physics, and you do this in statistical mechanics. So a number of these courses, you would actually connect these two. You might actually even do it in your engineering courses as well. So I'll put a little thing. I'll say that that the magnetic moment is directly proportional to the S. Okay, so now what happens is if this are a negative charge though, if this is negative, what would happen is that magnetic moment actually flips directions. And so what happens is if you had a negative charge, like an electron. So let's say here's our ball like this, it's spinning like this. So here's our S still. And if this is negative, that's not positive charge going that way. You can view this is negative charge going this way, which you can actually view as positive charge going the other way. So what happens is that the mu for a negative charge goes like this. What happens is there's actually a Q in front of this. So if you actually go through and work this out, there's actually the charge of the particle here times S. And since this charge changes sign, this actually flips. So for a proton, your spin and your magnetic moment are in the same direction. For an electron, your spin and your mu is in another direction. Okay, now here's the funky thing. Let's say instead I had a neutron. Here's a neutron. A neutron spins like this. Okay, what would be the magnetic moment for a neutron? Okay, we're getting a there wouldn't be one. Does that make sense? Because the charge of a neutron is actually 0. But guess what? You actually go through and you do some experiments. It turns out there's a very small mu and it's going backwards like that. And you can say, huh? The charge for this is 0. So there isn't any charged surface here, but guess what? It still has a magnetic moment. Now, here's an interesting question. Why does a neutron have a magnetic moment even though it has no charge? Okay, what are protons and neutrons made of? They're made of quarks. So protons and neutrons are made of quarks, which have a magnetic moment. Okay, so what happens is that a proton, so I can think of this as being made up of 3 quarks here. I don't remember what the quarks are for a proton. There's always 3 of them. A 3-quarked object. Okay, just so all the names in particle physics are really, really stupid. Okay, so a 3-quark object is called a baryon. Be honest, that name isn't entirely done. This is for the Greek word for heavy, baros, and that's where it's coming from. The word quark is absolutely stupid. That comes from a novel by James. There are 2 people that independently propose that quarks exist, Gell-Mann and Zeig. And it turns out that Mary Gell-Mann's name won. Zeig was calling them aces, and he was calling them quarks. So it turns out that the quarks comes from a James Joyce short story, Finnegan's Wake, where it says 3 quarks for Muster Mark, and he thought that would be a great name to name them. Okay, here's a life lesson. Okay, how do you know you made a mistake? You know you made a mistake when you've gone to a library and you pulled out a book and it's written by James Joyce. So what you happen to do if you're in a library and you pull out a book written by James Joyce? The answer is quite simple. You put it back on the shelf and you get a book that wasn't written by James Joyce. There, we've solved a life lesson. Okay, so the fact that these protons are made up of 3 quarks here, that gives rise to the magnetic moment. And this one here is made up of an up, and down quark. Okay? Yes. Okay, so the neutron itself, okay, that is made up of 3 quarks again, and this is a down, down, and up quark. Okay? And so what happens is that even though the neutron has no net charge, if you remember the charge of a down quark is minus a third the charge of an electron, and the charge of a up quark is 2/3 the charge of an electron. So this has a net charge of 0. This has a net charge of 1. Because these individual quarks have magnetic moments, that's why this actually has a net negative magnetic moment. It's actually pretty cool. Okay, now how does this connect to NMR? This is how it connects to NMR. So other questions for this? Okay, so let's look at an NMR unit. So first of all, there are 2 magnetic fields. In an NMR device. Okay, I'm not trying to make fun of the chemist, and I'm not referring to a chemist here. It's actually where I was up at before. The school I was at before, there was actually a very good organic chemist who one day dropped into my office and he went, Roger, do you realize there's 2 magnetic fields in a magnetic in an NMR device? And I was kind of said, well, yes. And I was really kind of bothered because I don't know how you could go along being an organic chemist for so long. And he was actually quite talented without realizing that there are 2 magnetic fields. That was bizarre. Okay, so we're going to have this external field here, this really, really big one. Okay, so we're going to have like a big one up like here like this. So this is the North Pole. This is the South Pole. So that's your first magnetic field. Okay, we'll call that B naught. And inside here is where you're going to put your sample. So inside here, there's your tiny little solenoid like this. Actually, I'm going to make it a little bit bigger so I can draw things. So here's my little solenoid. That's where your sample is going to go. And we have something like this. So that's a solenoid. Your sample goes inside here. So this is your sample. So what happens here is that right now, if there's no current going through that solenoid, what's going to happen? Well, we know that this torque is going to be mu cross B, okay? And what's going to happen is that if here's your sample, the protons are going to align with that field. Remember, this always is going to take the mu and try to align it with the field. So what's going to happen here is that if here's your mu for your proton, and here's your magnetic field like that, it's going to try to take this mu and align it with the field. Okay. So what happens is you put it in there, all the mu's are going to align with that field. Now what do? You send a current going through here like this. That's a current. So what's going to be the magnetic field associated with this current? Well, this is around a solenoid. So what do? You wrap your fingers around the direction that that current goes, and this produces a magnetic field like this. That's going to be the B from the solenoid. Well, what is that going to do? Well, this B from the solenoid, if I put it in here, now there's 2 magnetic fields. There's this guy and then this guy. That one's going to put a torque on these, and it's going to take these mu's and try to align them with that field. So what you put this on here, then those mu's actually align with here, and then you stop the current. So what happens here is you now have this device here like this. So you put this on here. So now if I look at the sample here, here's your sample here. The mu's for these are now going this way. That's your mu for the sample, and here's still your external field. Now, if I stop that field, what's going to happen? If I stop that field, I'm going to have a picture like this. That's what's going to happen. Okay, because you stop the field, now the mu's are still going like that. What is now going to happen? Well, those mu's that are going like this are now going to align with that field again, to go back to that original case. Hey, but what happens? and I'll give you a hint, you're now pros at this. If you look at that solenoid here, right, and here's your external field. If here's your little mu initially going like that, and now it's going to swing up to here and I'll go like that, what's going to happen in this loop? So if you have the mu's going like that, you're going like that, what's going to happen in that solenoid? There will be a change in the magnetic flux. Exactly, right? There's some magnetic flux through this solenoid because of those mu's. What's going to happen? Well, they're going to align like that. That's going to cause the flux through that magnetic in that coil to actually change. That's going to induce a current. So you're going to get some sort of induced current here. I'm just going to draw it like that. This is some sort of induced current. And you can actually measure this because this would be hooked up to some device. Now it's going to take a certain amount of time for the spin to flip. And how much time it takes to flip depends on basically how strong that magnetic field is. And so what happens is if you look in that field, so if you look at actually this, if here's your sample. So I'm making a big picture of the sample. What's going to happen? You're going to have all these atoms here. These are all these different atoms here. These are atoms in the sample. And what's going to happen if you look at, let's say the mu's for these guys here, the mu for this guy here, how it's going to flip actually depends, right? This is going to see some sort of magnetic field from these other electrons spinning. So the magnetic moment that this guy, the magnetic field that this little guy here sees is actually due to all the other neighboring things around it. And that's going to influence how long it takes for that to flip up. So what happens here is that if you measure how long this takes to flip up, that tells you a lot about what's around that other atom. And if you put this together with then kind of other things you know about the sample, you can actually start determining this atomic structure. So what you do is you put the sample in a magnetic field to begin with. They all align with the external field. You put a pulse through here that flips your spin. You stop the pulse. Eventually they flip back, but it takes a finite amount of time. And how long it actually takes to flip depends on basically the neighboring magnetic field that this little guy sees. And from that, you can start determining structure. It's a lot more involved than that, but that's the basic idea. In grad school, I had one entire course on NMR. I didn't have to take it. I took it because the fellow who did it was actually a world-class expert. His name, sadly, he passed away a couple of years ago. His name was Charles, but everyone called him Charlie Slichter. If you're an engineer at some point and need to know more about NMR, get his book. It's called Principles of NMR. It's absolutely brilliant. The only thing more brilliant than the book was actually him as a lecturer. He was absolutely stunning as a lecturer. I learned so much from him. But that's actually the basis for it. Are there any questions? And good grief, is that almost time up for class? Good, oh wow, class is all over. Okay, so we'll stop here today. I'll have office hours later today. I'll send you the link for it. I apologize for not having them yesterday. It turns out something came up that I wasn't counting on. And so we have office hours today. We have a test next week. And guess what? You're all invited. Isn't that great? Okay. And then, which we said it would be on Wednesday. And I'll tell more, the practice test is up so you can look at that. So have a great day and a great weekend and see you on Monday. Bye-bye.